Hi everyone. Today we're excited to have Dr. Ryan French, a solar physicist at the National Solar Observatory in Boulder, Colorado, speaking to us about his work on solar flares. So I've known Ryan for quite a while now, as he completed his PhD down the road from me at University College London's Mullard Space Science Laboratory. Now that's a mouthful. So yeah, Ryan's a fantastic science communicator, having given many public talks, and he also appears on TV a couple of times. So yeah, and he's also recently written his first book titled The Sun, A Beginner's Guide to Our Local Star. And that's set to be published in May, so we'll be sure to check that out when it's released. And then for today's seminar, he'll be presenting his work on spectroscopic and spectropolarimetric insights into reconnection dynamics in solar flares. So whenever you're ready, Ryan, please take it away.
Cool, that was a very kind introduction, Emma, thank you. Yeah, I mean, the first time Emma and I met wasn't under probably the best situations. maybe Emma can fill you in on this, but I bumped into Emma like a couple of times in London. Wasn't really friends with her, but I'd seen her around. And then I think you were at HEO for the solar physics summer school, the Heliospec summer school. Yeah. And I was visiting HEO at the time. I wasn't a part of the summer school, and I left one day and I saw Emma. Yeah, so I ended up going with hospital.
In the car park. I had to go to hospital.
In a bit of a state.
Oh. So yeah, Ryan accompanied me to A&E.
Yeah, so the first time I met Emma properly, it was me taking her to the emergency room. So she can fill you in on that. But anyway, happy to be here. Thanks for inviting me. As Emma sort of said, today we'll be covering, and why can't I change slides? Here we go. So, okay, I'm going to try and cover a few different things. So I'm going to start off with some content that actually is sort of pulled from my book. So talking about a very brief history of sunspot observations, and then I'm going to tie that in seamlessly, hopefully, into some basic physics of standard eruptive flares, magnetic reconnection, just some basic introduction. Not sure how much everyone in the room already knows about solar flares. And then we'll be getting onto some science a bit later on in the talk. So, okay, so let's begin our journey today, way back in 1128 in the town of Worcester in England. So there's a very big cathedral in Worcester, right? And a bunch of monks living at this cathedral in Worcester over about 200 years, they recorded a very in-depth history of England at the time. And it's one of the best historical records that we have. And in this 200-year massive book of history, there are only 7 pictures included in that 200-year history. One of them, for example, is of the death of the king at the time, King Henry I. There are a few sort of biblical drawings of Jesus and so on. But one of the drawings that they made out of these 7 is this drawing here on the right. Now, I want you guys to imagine for a minute that you're not physicists, but you are monks in Worcester, okay, in 1128. You wake up one day doing whatever it is that monks did in 1128. You walk outside and it's a hazy day, right? It's sort of foggy, it's hazy. The sun is just rising above the horizon. So because of the sun being low in the sky and the haze, you're able to look at the sun without sort of burning your eyes or anything like that. And what you see is this here. Now, I know you can all speak, I can hear you, so I'm actually going to ask for some input here. Imagine you're a monk, okay, at the time, and you see this on the sun, like a massive black spot on the sun. What do you, as a monk, think that you are seeing? Like, use your imagination, right? Yeah, right.
Yeah, what's wrong with the sun?
Yeah, what's wrong with the sun? Like, maybe you think the sun is breaking. I think there's a hole in the sun, there's a demon on the sun, a dragon, I don't know. Whatever you might have thought. At the time, it was sort of heresy to suggest that the sun and the stars were anything less than sort of perfect. So they recorded this in the book, but they didn't really put any interpretation of what they were seeing. They sort of just drew it and then moved on. And this was the first evidence of sunspots, the first observation of sunspots. And you can see these sunspots that they saw at the time were clearly big enough that they were able to make out not only the dark sort of umbra of a sunspot, but also the penumbra as well. And they even managed to draw some structure on here. So really interesting that these guys working as monks back then were able to see this. And this is pretty much the only sunspot that was ever observed from pre-telescope era. But after the telescope was invented in 1610, telescopes were pointed at the sun without any filters, is what I learned when doing my research for the book. Like Galileo just pointed a regular ass telescope at the sun. Yeah, which is kind of bonkers that he managed to do that. And this is a drawing. I forget which year exactly, but the early years of the telescope, some nice drawings of some sunspots. You see far more accurate than the earlier Monk drawings. But even though observations of these things became more frequent, scientists were still really unclear what sunspots actually were. The first sort of suggestion came from this German astronomer called Christoph Scheiner, and he suggested that these weren't actually a part of the sun, but they were some small planets orbiting closely to the sun. In the same way that sort of we can see exoplanets through sort of sun transits, that's sort of what he thought he was seeing here. Galileo proved him wrong, and he proved that these objects were rotating with the sun, so they weren't separate to the sun. And he suggested that maybe these were cloud-like structures in the atmosphere, like analogous to the clouds that we have here on Earth. This was disproved again when it was found that these were actually quite low in the solar atmosphere. And this Christoph Scheiner guy piped up again, and he said that these weren't clouds, but these were dense objects embedded in the atmosphere. So you can sort of picture his analogy was like the ocean moving around islands, for instance. These were dense structures sat in the sun. And it was about 100 years later when William Herschel came along. William Herschel, very famous guy, discovered the planet Uranus. Neptune, sorry, was William Herschel. And he did some temperature measurements, and he suggested that these weren't islands, they weren't clouds, but they were sort of openings in the atmosphere that allowed you to see through and see a cooler sort of underneath layer of the sun. And what we know about sunspots today, right, is these are regions that have suppressed sort of thermal convection, so they're able to cool to colder parts or colder temperatures than the surrounding parts of the sun. So it was sort of along the right lines, except as you can see here, this wasn't the full quote, because the full quote from William Herschel was that these are openings in the sun's luminous atmosphere, allowing a view of the underlying cooler surface of the sun, which is likely inhabited. So William Herschel, one of the most accomplished astronomers of all time, thought that there were aliens living on the sun. So if you ever feel like you've made a mistake in your science, it can't be as big as this quote here, so don't worry about it. Okay, so we'll fast forward a little bit now as well to 1859. Now, 1859, a very famous year for solar physicists. This man on the left is a man called Richard Carrington. He was sort of an amateur astronomer. He built his own observatory around that. He was also a brewery owner as well, so a great job combination there. And he would look at sunspots every day, trying to track or try to measure accurately like differential rotation on the sun. That's what he was meaning to do. And one day he was observing the sun, and he saw these bright points that were the white light, so bright to him looking through the telescope. He saw them appear over the sunspots. He watched it for about half an hour. He watched these bright regions sort of move and evolve across the sunspot, which we now know to be sort of flare loops. And he recorded this. He thought maybe this is important. I'm the first person to see this flash of light on the sun. And then the next night, the aurora was seen all the way down to the south of the USA. The Caribbean saw the northern lights. Florida saw the northern lights. Southern California saw the northern lights. It was seen everywhere. There are stories of miners in Colorado and California like mistaking the bright lights for sunrise and like waking up and starting to get ready for the day, but it's actually the middle of the night. And there are other stories as well of Europe, who was in daylight at the time, telegraph machines going wild, generators sparking, all sorts of weird and wacky stuff, which we now know to be a result of a coronal mass ejection, right, which traveled from the sun, from this flare, and arrived at us here at Earth. But at the time, they had no idea what caused this. They still had no idea what sunspots even were. And it wasn't again for another few decades till 1908, when George Hale, again, very famous man, he pointed a telescope at sunspots measuring spectra and found the splitting of the spectral line. This is something called Zeeman splitting. And from this, he was able to say, okay, sunspots have very, very strong magnetic fields, many, many times stronger than the Earth's, thousands of times stronger than the Earth's. And that is what is causing sunspots. So it was only just over 100 years ago that we even realized what sunspots were, right? They're super dense regions of concentrated magnetic field, and the magnetic field lines that flow almost, you can picture it as a bar magnet, form these coronal loops that we see in extreme ultraviolet observations. But even though back in 1908, he had found out that sunspots were magnetic, that still didn't really explain how magnetism on the sun could impact, the aurora telegraph machines here on Earth. And that discovery again, and it shocks me how late these things were discovered, but the discovery of CMEs didn't even come until around 1970. And here we go. So it was actually 1964, before we'd actually seen CMEs with observations, that the standard eruptive solar flare model was first introduced. This was introduced by a bunch of guys, 5 different guys, who are often given credit for the acronym of the name of this, but it's just the eruptive standard flare model. Now, in 2 dimensions, the flare model looks something like this. Of course, the sun is not 2D. This is an oversimplified cartoon, but it does a really good job at pinning down and explaining some of the basic phenomena that we see in solar flares. So a solar flare will sort of be initiated. We have some sort of overlying magnetic structure, such as this flux rope here, and then above that, you have an overlying magnetic field. If underneath the sort of magnetic structure, your field lines are pushed together, you have a situation where you have your oppositely orientated magnetic fields, and magnetic reconnection, which we'll explain a bit more in a minute, can occur here. And this allows the magnetic fields to reconfigure themselves, separating magnetic fields at this erupting structure, and this thing will fire up to be a coronal mass ejection. And then below the reconnection site, you form your flare loops. We expect to see hard X-ray sources at the top of the flare loops. So that's one phenomena. We see the CME erupt, of course. We see flare loops themselves. They're very bright in extreme ultraviolet and ultraviolet emission. But also what we see is that where the magnetic field reconnects, you get the acceleration of high energy particles running down the magnetic fields. And where they collide with the chromosphere, which is a layer of the sun's atmosphere, they collide with the denser, cooler plasma of the chromosphere, causing it to glow. And where this glows is the intersection between sort of the flare loops and the chromosphere. We call these flare ribbons. And in 3 dimensions, you can see this model a bit better of how it is in reality. At this point, instead of reconnection happening in a single X point, you can actually see that reconnection occurs along this entire 2-dimensional sheet. And this 2-dimensional sheet is what we call the current sheet. And this is where reconnection can take place. You can see again the overlying magnetic fields over this flux rope. These reconnect to get your flare loops and then the field lines contributing to the CME. And you can see now that the flare ribbons are quite long in shape and always connected in some way to the current sheet and to the flare loops. Excuse me. But what the standard model cannot sort of explain, what it doesn't address, is the actual nature of what happens in this current sheet region. The standard model just says field lines come in, field lines come out. What is actually happening in this little black box, if you will? Well, this is sort of a fairly simple cartoon of magnetic reconnection. You have your oppositely orientated magnetic field lines. They're flowing together to a point. And when they cross over into this box, which is the current sheet itself, magnetic fields no longer act in the same way they do outside of this box, right? You go from an environment where you have magnetic field lines, plasma flowing along the field lines can't cross or anything like that, to in this region where magnetic fields essentially diffuse. They can sort of blend into one another, and it's not sort of the standard picture of how field lines behave inside of this region. But out of this region pop newly reconnected magnetic field lines, and they flow outwards, sort of perpendicular to the direction that the magnetic field flows inwards. And this reconnection scenario will keep going on and on and on, as long as you have new field lines entering that little black box in the middle of this current sheet. But as to what a current sheet actually looks like or how it's structured, again, there's been a number of different models to explain this. The first came by Sweets and Parker way back in 1956, I believe, and they proposed Sweet-Parker reconnection. These were the first guys actually to propose reconnection as a concept, and they said that reconnection will occur basically all the way along the full duration of your magnetic field. Now, this works in principle. However, when you do like the maths and the modeling of this, the amount of energy that can be released from this process, or the rate of energy release, I should say, is far slower than the rate of energy release that we actually observe in solar flares. So this scenario can't be happening in reality on the sun. So Sweet Parker reconnection was built on later by Petchek reconnection in 1964. And he said that instead of reconnection occurring along the full extent of your current sheet, it just occurs at a small point in the middle, and you have these sort of slow mode shocks that sort of accelerate the input of new field lines into this region, allowing you to get faster reconnection. Now, Petchek reconnection can account for the observed rate of energy that we see being released in solar flares. However, it's not clear whether such a configuration of these slow mode shocks is sustained in solar flares, or whether, even if it can be sustained in principle, whether or not it's being sustained in every solar flare that we see, right? They're two different things. So building on this again, in recent years, attention is starting to turn to something called the tearing mode instability. Now, the tearing mode instability happens if you have a current sheet whose length greatly exceeds its width, then it's going to become unstable and sort of collapse at sort of incremental points along the current sheet, forming these mini reconnection sites. This mini reconnection or reconnection happens in this small site here, and you form something called these magnetic islands. And if you were to zoom in once again at this magnetic island, you once more might have a situation where the length still exceeds its width enough for it to collapse again into even smaller islands. And then you begin to get a turbulent sort of cascade of these islands breaking down to smaller and smaller structures. Except if you move out of 2 dimensions, this gets a bit more complicated. Because remember, at each reconnection site, not only do you have the inflow of the magnetic fields, you have the outflow of the reconnected plasma as well. So as soon as you have your plasma firing out of these mini regions, you are no longer going to have a situation with these nicely lined up islands. You're going to be churning your field, you're going to be getting more turbulence, and not only are your islands going to break down into smaller islands, some smaller islands might reconnect with bigger islands, and you get the growth of islands as well, which is an important point as well. So in simulations and in theories, this tearing mode instability, it works in simulations, right? And it's able to account for the rate of energy that we see in solar flares. However, observational evidence is sort of lacking. Observational evidence that is actually taking place on the sun isn't concrete. And so that's where the science goal of my work comes in, is to use a range of ground and space-based instrumentation to basically investigate the role and the nature of reconnection in a couple of different solar flares, and in particular, searching for evidence of this tearing mode instability. Okay, cool. So let us begin with this very famous flare from September 10th, 2017. Let's get my pen back. Let's play this. Happens really fast. This is a really famous flare. It's actually the most published solar flare of all time. This is a little map just on the right here, just to show you every pin, every red dot is an institute that has an author that's published on this flare. Pretty sure you guys probably, is this you guys? I don't know, maybe you're a bit further. I can't remember if you were on there or not, but a lot of institutions researching this flare, which is really cool to see. And let me play that movie again here. So it happens really fast. We see it shoot right off the western edge of the sun. It was basically the only active region on the sun at the time. So every telescope was pointing directly at this region and captured it as it erupted. You can see as well the scale of this thing, the CME erupting out into space, and behind the CME, as you can see in these observations, we see this sort of laminar horizontal sheet of plasma, which again extends all the way out very far into the corona. Now, what we're seeing here that's been shown from various studies is that this heated sheet of plasma, super, super hot, it's turbulent, and this is most likely heated plasma around that current sheet region, sort of beneath the extending CME, which sort of makes sense in the picture of the standard model. So I'm not going to call this, I'm not going to call it a current sheet, because current sheets are smaller theoretically than you can actually observe. but this is heated plasma around the current sheet. So I'll refer to it as a plasma sheet from now on. So there's been a lot of different studies of this plasma sheet region. Oh yeah, here we go again. So just a close up of a few frames breaking down. You see the cavity starting to erupt. You see me shooting out into space, the plasma sheet behind it, and behind that, the flare loops. So really closely matching that two-dimensional or even three-dimensional cartoon that I showed you earlier. So there's been a lot of studies looking at this plasma sheet, trying to search for the role of the towing mode instability in this event. And some studies have looked at the velocities, sort of the turbulent velocities in this thing. They've looked at the temperatures of this thing. They've looked at sort of power laws of small stuff flowing out of this thing. But what none of these previous studies address is actually, what the magnetic field is doing in this plasma sheet. And ultimately, the magnetic field is the main driver of magnetic reconnection, right? And the main driver of the towing mode instability. So that is where we get on to spectropolarimetry. So I don't know if many of you have done polarization, especially in the context of the sun, but basically imagine we have a chunk of plasma sitting above the edge of the sun, right? That chunk of plasma is being radiated from the sun. It's being radiated anisotropically. It's getting radiation from the sun's photosphere, but nowhere else. So when you give that chunk of plasma anisotropic radiation, what you're going to do is sort of the electrons and the position of the electrons in that plasma, they're going to become polarized, okay? And what do I say here? Yeah, generates unequal populations of magnetic substates. That's just your atomic polarization. And that polarization that chunk of plasma has depends on the local thermal conditions, depends on the density of the plasma, how often these ions are colliding. But it also depends on the magnetic field as well, because plasma, as you know, is sort of frozen into the magnetic field. So for the ion 13 pairs that we'll look at in just a minute, the linear polarization is proportional to this expression here. So 3 cosine squared theta b minus 1. Now, when that plasma, which is atomically polarized, emits light through collisional excitation or whatever, that light that we can then measure from Earth will be polarized by the same degree as the atomic polarization. So this equation here. Depolarization can occur via collisions. If your plasma is colliding, you're going to destroy that polarization information. But otherwise, your polarization is going to be proportional to this theta b. And this theta b is the angle between the magnetic field and sort of the direction that light is coming. So it's the angle between the magnetic field and the radial direction from the sun. So how can we utilize this linear polarization? Well, there's a small telescope based up on Mauna Loa in Hawaii. It's called COMP, the Coronal Multi-channel Polarimeter. It's tiny. It's a 20 centimeter telescope, which is kind of bonkers to me that it's so small, but we're able to do such cool stuff with it. The spatial resolution is not fantastic. It's 4.5 arc seconds. The temporal resolution, again, is not good either. What it observes is this iron 13 pair of 2 lines that are density sensitive. So by calculating the ratio of these lines, you can calculate the density of the plasma that's emitting it. It can measure Stokes Q and U, which are your 2 linear polarization diagnostics. And by taking Q and U, we can calculate P, which is the amount of plasma, or the degree of polarization. So it's like the fraction of the light that is polarized. And you can also calculate theta as well, which is the angle of that magnetic field, although there's some ambiguity there as well, and we won't be talking about this quality. We will be focusing on P, which is the fraction of linear polarization. Okay, so let's get a closer look at this flare. So top left, this is an image from the telescope I showed you previously, or the movie I showed you previously, I should say. So this is EUV, just an imager, and we can take a cross section through this bright plasma sheet region. As we expect, find a very clear spike in intensity at the location of the plasma sheet, right? If we look at the intensity measured by COMP, so we're looking at infrared now, looking at slightly cooler plasma, there's no significant contribution of the plasma sheet in intensity, which is interesting. But when you look at the linear polarization, P, this is what we get up here, something very, very different. And now what we see is we see a dark sort of small semicircle peeking over the coronagraph, composite coronagraph, by the way. And this sort of small semicircle aligns with the top of the flare loops, which we see. We see this dark triangular structure, which I'll explain in just a moment. And we also see above this dark triangular structure, this sort of broad horizontal dark feature here. And when we take a cross section through that, we once more find a very broad and wide dip in polarization, but the minimum polarization is at the same location as the plasma sheet. It's sort of spatially in the same place. And worth noting as well that the minimum polarization we see is about 1%, and that too is important. So the question is, why is the linear polarization so low in this flare? And what can that tell us about the flare? Well, we can calculate the density in this region from looking at both of the comp lines, the iron 13 lines. And what we find is that the density is not high enough to produce the depolarization via collisions. Up in the flare loops down here, the flare loops are very, very dense. So you've got a lot of collisions that can destroy polarization to these levels. But up here in this triangular structure and this broad feature sticking out here, density, collisions is not the cause. So what this means is that our low polarization must be due to this expression here. So the 3 cosine squared d to b minus 1. And just in a few cartoons here to sort of illustrate what that expression looks like. If you have a phi to b equal to 0, so your magnetic field is radial away from the sun, then your polarization is going to be at a maximum. Okay, and that maximum will depend on a few different things, but your polarization will be at a maximum. There'll be no depolarization. If, on the other hand, you have magnetic fields that are tracing this angle of 55.7, if you set p equals to 0 and solve for phi to b, you'll get this angle of 55.7. So this is the angle at which there is no polarization due to this expression here, and we call this the Van Vleck angle. So this larger dark triangular feature here, this is just where the magnetic field above these loops is tracing this Van Vleck angle. So again, we can explain this from this expression pretty simply. The third sort of box that I show here is that if for each pixel, okay, if for each pixel you have a variation in magnetic field within that pixel, then the polarization that you measure is going to be somewhere between 0 and the maximum value, and that value will depend on what the magnetic field is doing inside of that pixel, if that makes sense. Now, because there's no way that just up here the magnetic field could be tracing this angle just here and nowhere else, this is starting to seem like a pretty likely scenario. So what we can do is to jump into some simple empirical models with, this is called coronal line emission. It's a program that can simulate the polarization of different sort of scenarios in the solar corona. So we set up these small boxes. These are just simple empirical models, that no MHD here or anything like that. But in this first scenario, we just set a massive chunk of plasma orientated in the same angular direction that this current sheet is pointing out into space. And if you do that, as we expect from this cartoon down here, there's barely any drop in polarization if this were the case. Our second scenario is that for each pixel in this 3D box, so there's pixels in the line of sight as well, we just randomly set the direction of the magnetic field. Okay, this is not physical, of course, but just a little, little thought experiment. Let's randomly set the direction of each pixel, and maybe this is something like what you might expect from sort of a turbulent system here in the current sheet. And if you do that, you get, obviously it's random, so depending on where you cut and which time you run it, you're going to get slightly different values. But we see a decrease in linear polarization to around the 1 to 3% range. So suddenly we're in the ballpark of the 1% range that we see in comp. I should note as well, these experiments are simply looking at the minimum polarization. We're not trying to address the gradient or the slope or anything like that. So that brings us then to cases 3 and 4. Now, in this case, what we do is we set line currents in the line of sight. So just currents in the in the line of sight of our box here. And what this does is it creates these sort of circular or cylindrical magnetic field structures around them, sort of replicating what these magnetic islands might look like within the plane of the sky. We do two cases, one where these magnetic islands are too small to resolve by the resolution of the telescope, and one where these structures are much larger as well. And what we find in the case where these structures are unresolvable, so these islands are too small for us to make out a full island like we do in the bottom panel, we're able to destroy polarization down to a rate of about 1%, which is matching what we see in COMP. Now, this is sort of exciting. And this was the first paper that I did in my PhD back in 2019, but basically to demonstrate that unresolved magnetic structure is capable of destroying polarizations down to the level that we see by COMP in this event. And we also showed that these observations are consistent with the theories and models of the tearing mode instability in the plasma sheet as well. What makes this more exciting is that DKIST, which is a telescope based out in Maui, which came online this year, and people have started getting data coming in for that. DKIST is also able to observe these same iron 13 pairs with a 4-meter aperture instead of a 20-centimeter aperture. So the amount of photons you're going to be getting from DKIST as opposed to COMP is going to be bonkers. Much higher signal to noise, better spatial resolution, better temporal resolution. So we'll really be able to start to push these coronagraph studies of flares further as well. But the September 10th, 2017 event, as I said, was a very special set of observations. Everyone was pointing there at the same time, a very fortunate data set. And we can't just wait for a once in the solar cycle flare anytime we want to learn something. So what can we learn from more frequent observations or observations of flares that are perhaps more common? So this brings us now to flare ribbons. If you recall, we have the reconnection site, and the flare ribbons are where the particles coming out of the reconnection site intersect with the chromosphere and with a marked emission in the chromosphere. Now, as I sort of said from that description, due to the magnetic connectivity between the ribbons and the current sheet, behavior in these flare ribbons must reflect processes happening up here in the current sheet region. And so the aim of one of my more recent papers is to search along this flare ribbon for sort of the appearance and the behavior of spatial brightening, so small bright points along these ribbons, and to sort of try and infer from the behavior of the ribbons what is happening up here in the current sheet. So stepping away from the September 10th, 2017 flare, which was almost an X10 flare, we're looking at this study a B1.6 class flare. So this is almost 10,000 times less output than the September 10th flare. So as different as you could get almost between two flares. A very small brightening right in the middle here of an active region. You almost wouldn't notice it if you were looking at a full sun image. But the reason we picked this flare is because it was observed by IRIS, which is a NASA small explorer mission launched back in 2013, I believe. IRIS measures the chromosphere and transition region. It has a slit jaw imager where it can observe a larger part of sort of the sun, and it has a slit which you can measure spectra from. In this case, these are images of the flare ribbons. You can see the location of the slit. You can see it's slightly brighter here where we have the slit. So we have imaging everywhere in this field of view. Obviously, it's an image, and spectra just where this slit crosses the ribbon here. And the reason we picked this data set is because it was observed with a 1.7 second cadence, so really fast. And what we see in the IRIS perspective is these two ribbons. We've got an east ribbon, the brighter one, or the bigger one, the west ribbon, the smaller one. They brighten together, they dim at slightly different rates, but brightening together is the key, this left plot here. After we see the peak brightness, we start to see in AIA, which measures the atmosphere, we start to see these flare loops between these two ribbons. But the most important thing is that if you look at the magnetic flux traced by these ribbons, so the area of the ribbons multiplied by the magnetic field down in the photosphere, we find that the magnetic flux traced by both ribbons as the ribbons grow is the same. Now, the reason this is important is because this tells us that the flare here, we are reconnecting magnetic field lines that are going from one ribbon to the other, but there's no magnetic field lines reconnecting with any higher altitude structure or something connected to another part of the solar disk, and there's no CME erupting into space. Basically, we know for certain from this plot that the field lines between these ribbons are reconnecting, and that is all. There's nothing erupting, nothing else happening. Okay, so skip this slide. We implement a tracking algorithm to track the centroid of these flare ribbons as they evolve in space and time. And the reason we want to do this is to be able to plot the intensity profile along the center of the ribbon. We do this at every 1.7 seconds interval. And then we take this signal here and we calculate the fast Fourier transform of this signal to try and find the spatial scales that these bright points are sort of separated by along the flare ribbons. And once again, we do this at every 1.7 second time step. And if we combine the image that we get the intensity cross section, we combine every time, fast Fourier transform, we combine every time step, we can put together these images, which is sort of these stack plots of the full evolution of the flare. So the left here is intensity. So each vertical cross section is just the intensity along the ribbon. So you're seeing how the brightness changes along the ribbon with time. And on the right here, each vertical cross section now is the fast Fourier transform of the corresponding sort of position in the left plot. So you can sort of see before the flare happens, there are sort of bright points that aren't related to the flare that are separated coincidentally, sort of at an interval of around 2.5 megameters here. Then as the flare kicks off, everything sort of changes, you can see. It's important to note that as we get to the flare, we see what appears to sort of be very quick, this is log plot, right? See the very sort of rapid exponential growth of spatial scales along the flare ribbons from what, about 1 to about 6 megameters sort of in size. And as you can also see, they start growing at slightly different times. There are different structures here too. Okay, so then what we can do is we can take our plot. So this again is the fast Fourier transform at each position or each time along the flare ribbon. We can pick any spatial scale, right? So we say 1.75 megameters. We pick that scale, and now let's take a look at what happens to the sort of the power of that spatial scale along the ribbon as the flare evolves. That's this middle plot here. We start off sort of below the noise level, so not much going on. And then as you can sort of see, even just from the color scale, we see this exponential growth up here to the peak of the flare. And if we fit sort of an exponential curve to the growth here, it will tell us the start time of the exponential growth and the end time of the exponential growth as well. And we can calculate this at every different spatial scale that we see along the flare ribbons. And if we put them together in a plot, this is sort of the crux of the work here, is what we see is this spatial scale of about 1.75 megameters starts growing before anything else. So if you imagine the flare ribbons, we see these bright points separated by about 1.75 megameters. They start to grow, followed then by the subsequent growth of both smaller spatial scales and larger spatial scales as well. And we see this in both ribbons simultaneously. So the fact we see this in both ribbons tells us that the growth of these sort of spatial features at this rate is related to something connected in common to both of these ribbons, and that must be the reconnection site up at the top of the flare. Now, the fact that we see the exponential growth and evidence here of this cascade and inverse cascade to larger and smaller spatial scales is solid evidence of the tearing mode instability in the solar flare. So you remember at the start, you have those magnetic islands that form. It will collapse to sort of a preferred spatial scale. That's the size of the magnetic island. And as that island begins to collapse, you get smaller scales forming. As they begin to coalesce with larger islands, you get larger scales forming as well. And that's what we're seeing here. Now, this plot compares, this is the cyan and magenta curve are the same curves as the figure before, just rotated on their side. So we're looking at the spatial scales versus the time. And this black curve is the non-thermal velocity or the line width that we see from the spectral observations from that position in the ribbon. If you remember, we have spectra there. And what we see is that the growth of these spatial scales, which are really subtle, precede the growth in the turbulent velocity by about 15 seconds. And similarly, when our exponential growth ends, about 15 seconds later, these velocities start to decay. So this is suggesting that the plasma turbulence that we're observing in the form of these non-thermal velocities in the chromosphere is being driven by this tearing mode instability within this confined flare. And to take this one step further, just to give another really solid argument that this is what is happening, we can then return again to our fast Fourier transform maps. And this time, just look at a given time, look at the power law spectrum that you're getting as the power output of your fast Fourier transform. The different colors here equate to different times in the evolution. The tick marks also match the ticks on this plot. So what we see is the yellow dash here. So the red dash isn't shown. Before the flare happens, there's no sort of power law at all, right? It's a sort of noise down here. At the time that our spatial scales start to grow, we see a hint of things starting to grow here, specifically in our preferred spatial scale, it's 1.75 megameters. By the time we get to green, this green curve, everything has started to grow across all spatial scales. So we now have this power law rising in power. And by the time we tap out, which is at the peak of the exponential growth, we get this cyan curve, which we're basically fitting a power law here. Now, this is interesting because in turbulence, or you expect to see power laws in turbulence all the time, but the specific power law that you get will depend on the type of turbulence that you are seeing. And the fit of this line here to a line of 2.3 is consistent with simulations of tearing mode induced turbulence, which predict a power law of 2.3 for turbulence triggered by the tearing mode instability. So once more, this really confirms to us that the tearing is happening within this flare. And again, this is just one flare, right? So part of the work I'm doing at the moment is expanding this to a larger list of events. But here we go. To summarize that sort of second chapter, the behavior of spatial scales across a flare ribbon is consistent for this event with the presence of the tearing mode instability. And the timing is suggesting that the tearing mode is triggering the plasma turbulence to this power law of 2.3. And once more, this begins to shed light on, the interplay between reconnection, turbulence, current sheet, flare onset, so on and so forth. So that is the end of my talk. Some general conclusions here from the work. So we presented some new novel techniques which can be used to probe the nature of the current sheet without having direct imaging of that region. And for the two flares studied, which are very different types of flares, it seems like the tearing mode instability is most likely playing a very important role in this reconnection process. And finally, this methodology can be pushed further with the new DKIS telescope, which has started observing this, or I should say last year now, in 2022. And finally, just a little plug. This is a link to my website where I link the different sites you can buy this book. It goes over basically the history of observing the sun and then ties it into some modern science and how people can observe the sun at home as well. The publication date that Emma said in May is for paperback in the UK and ebook in the US. I think it'll be a few more months, probably the summer, till it comes out in the US in paperback. But yeah, thanks everyone for your attention and for coming along and for inviting me again. And I welcome any questions or discussion that anyone has. Thank you.
Yeah, thank you, Ryan. Do we have any questions, either online or in the room first? Oh, no, that's just a clapping hand. Tay.
I'm not even sure if I'm going to be able to construct this question coherently, but the tearing mode model.
Yep.
You briefly mentioned that the scale has to be such that for these islands that you labeled could be formed. Yeah. And obviously the second example that you presented that met that kind of sort of dimensional criteria, I guess, for it to be meshed with the numerical model. The other one, however, does it fall under the kind of dimensional scale that would be considered as a terrain model? The other one.
Right. So I think you're asking, does the spatial scales that we see in this flare match the sub-pixel scales from the other flare? Is that your question?
Yeah, let's go with that.
Yeah. If it wasn't, let me know. So it's an important thing to note. Let me find the slide here. So these spatial scales that we are observing in the flare ribbons, so I talk about this preferred scale of 1.75 megameters, right? This is not the scale that these things are collapsing up in the corona, okay? So you would obviously get your magnetic islands in the corona, but then by the time these things reach the chromosphere, you're going to be seeing a projection of that scale dependent on sort of the size of the configuration in the magnetic field, right? So in the case of the first flare, we're we're observing this region up here, and we're saying that these things are happening on a sub-pixel unresolvable scale. But by the second flare, so smaller events, we're observing these things as they're projected down into the chromosphere. So we can't really do a comparison between the spatial scales we see in the chromosphere and the subpixel scales up in the corona. Ideally, what you'd want to do, and what I hope to do, is sort of back map the physical scales that you see in the chromosphere to the sizes of these islands up in the corona. But to do that, you would need some quite accurate estimates of the field geometry up here, which we don't have.
Right. Thank you.
Yeah. Any other questions? Oh,
actually, I have a question. Like, could you explain why you, on the second case, you observed projected, like, feel like when it's like it's projected, like, basically observing at the foot of the flare, because as far as I know, it was like kind of, I could like how like you observe something that is projected.
Yeah. So sorry, you're a bit quiet. I think you're asking about the projected scales, right?
Yeah, exactly.
Yeah. So the reconnection happens up in the corona, right? Up in the current sheet region. And what we are seeing in the second case is what we're observing is plasma flowing out of this region and flowing down, hitting the chromosphere, heating up the chromosphere, forming these flare ribbons. Now here, I've drawn this to be fairly like straight, right? But we're essentially seeing an imprint of across the current sheet. But these flare ribbons, like this could be a lot wider, this could be really narrow, so these features could grow by the time they reach the chromosphere down here. Does that sort of make sense? I'll go back to this here again. So you have these scales, and as they go down to the chromosphere, that magnetic field could be expanding or contracting. And so the physical scale that you measure in the chromosphere is not going to be the same as what's actually happening up in the corona.
Yeah, but like if there is some magnetic like reconnection or terrain instability, what is like, how are you sure that the things that is happening at the top of the magnetic structure is going to happen at the feet?
Yeah. So you get this. Let me go back to this one again. So the stuff that happens here flows down the loops. Okay. So we know that what is happening in the ribbons must reflect in some way the behavior of these up here, right? Just because they're connected magnetically, and you've got the stuff flowing down. And by finding the power law, and well, I actually sort of skipped this slide. I'll explain this slide properly, right? So our two flare ribbons that we see are different sizes, right? The east ribbon is bigger, the west ribbon is smaller. So we can't do a direct comparison of the spatial scales we see here to the spatial scales we see here, because we wouldn't expect them to be the same. So what we do, because we know that the flux is conserved between the two ribbons, if you remember, we see the flux sort of is conserved here, so we know that you're not losing any field to anything else. What we can do is we can basically take the areas of the ribbon, square root the area to get like a length scale of both ribbons. And what we do is we use that length scale to scale the spatial features that we see in the smaller ribbon to that of the bigger ribbon. And only then, when we've scaled this western ribbon, we get the matching values here. So it's the overlay of these two curves, the fact that when you adjust for the size and the length of the ribbon, you get the same scales appearing in both. This is what reaffirms to us that what we're seeing here is an output of that common connection.
Okay, thank you.
Yeah, you're welcome.
Any other questions in the room? Oh, tell you
There's
again.
one more. The first case where you use a polarization to study the structure. Yeah, I think the earlier one had the slide before this, maybe more pictures. Yeah. I'm having a hard time understanding what the pictures are. So pictures are mapped out based on the polarizations measured.
So these are a zoom in of the flare region, right? So they're just an image like zoomed in here. So take this box. This is what we're seeing. So top left, this is EUV images. Yeah. So they're all images, right? So this is EUV images. This is image of the intensity from comp, and this is an image of polarization around the flare.
So it went like, we're looking at the sun, it went like this, but we're looking at someone that came this way.
Yeah. So maybe I cropped this flare, the picture a bit too much, but you can see the edge of the flare here erupting outwards. So it's right on the very edge of the flare. So this is like the black background of space basically behind the flare, which is very different to this event where you're looking straight down on the sun. So different vantage points.
We're picking up whatever scattered off and came towards.
Yeah, exactly. So in the case of this one, you're sort of seeing, we're looking at what's above the sun, right? You're looking at the coronal emission. But in the case of the other one, you're looking straight down. So all you see is the emission from these brighter foot points down here.
And what was the time scale of the video? Whoa, sorry.
So this video covers about 3 hours just here.
Whoa.
This whole thing's about 3 hours. Most of the flare, like most of that energy is released in the first 40 minutes, but it's slowly producing more energy over almost 24 hours for this flare. It's one of the longest duration flares. And here are some timestamps. So just before 1600, you see the eruption. Shortly after that, you see this plasma sheet forming. And then much later, by the time the saturation has died down in the image, you can make out these flare loop structures.
And different models that you have introduced, they are trying to describe that bright region, like what's happening there.
Trying to describe this horizontal plasma sheet, current sheet region. Yeah. So.
All right, that's all I got.
Yeah. Well,
just quickly, could you show again like the plots of the exponential growth? Just like at the time, like how long does the exponential growth last?
So this is a really small flare that we're seeing here. So this one is the order of like 30, 40 seconds. Okay. So this second smaller flare, tiny compared to that original flare, which, so we're talking hours versus a minute in terms of flare duration. Yeah.
Thank you.
If anyone else has any other questions, feel free to reach out to me by email or Twitter or whatever. Happy to answer anything else.
We're getting quite close to the hour now, so I think we should end it there and thank Ryan again.
Yeah.
Great, thank you so much, Ryan.